watching the second lesson on mechanical systems. In this lesson, we'll be talking about levers. This is a continuation of work and what work is, right? In the previous lesson, we talked about what work was, and that work was the amount of force needed to move an object a certain distance. Work was measured in joules, distance was measured in meters, and force was measured in newtons. And so we said, well, what can we use to make work easier? Well, simple machines, or machines themselves, make work easier. Now, they don't lower the amount of work needed. The work is the same, because it's moving the same distance. The load is, or whatever you're lifting. But it lowers the amount of force you need. So we'll go into more detail about this as we talk about levers. So here we see a classic example of a lever, the teeter-totter, right? You have this board here and this middle part here that we'll go into, and this lever will move up and down depending on how the weight shifts. So, what is a lever? A lever is a simple machine that we've talked about before, a machine that makes the force required to lift an object lower than it would be if you just lifted it yourself. So, a lever involves a flat bar, or a bar setup in any way, that sits on a fulcrum. A lever lets you change the amount of force needed to lift an object. Some classic examples of levers are wheelbarrows, scissors, tongs, even hockey sticks. These are all examples of different kinds of levers, and we'll be talking about those different kinds as we move forward. So, first is that levers have three important parts. You have your effort arm, your load arm, and your fulcrum. Right? These are the three parts of a lever you need to have and need to know in order to be able to build a lever itself. So when we look at this lever, and if I clear the ink, you can see that as this effort arm is pushed down, right, the load and the load arm moves up. Right? Just like in our definition, to lift an object. This affects how you lift the object, being this weight here. So let's talk about the key terms. We have the fulcrum. The fulcrum is the pivot point, or the turning point. So when you look at our lever, you find the point where things are turning or changing. That is your fulcrum. So in this picture, the flat board is turning on this triangle at this point. Right? So you would say that this is the fulcrum. Well, let's go back to our teeter-totter. The point of change, or the point of turning, is right here in the middle. So that's our fulcrum. We look at our examples here. When you lift a wheelbarrow, it shifts like that. So our fulcrum is there, right? This is our fulcrum. When you open scissors, these two arms rotate around this point. That's your fulcrum. Tongs, they rotate around this point, the fulcrum. Now a hockey stick doesn't seem to rotate at all. But imagine yourself hitting a puck with a hockey stick. There's a rotational axis that moves as you swing the stick, or as you do a slap shot, and that is where the fulcrum would be. And we'll be talking about that in more detail. So, fulcrum is the turning point. The effort arm, kind of self-explanatory. The effort arm is where you're putting effort. This is where you're putting the force in. This is where you're going to be pushing down onto the lever, and in some case pushing up, right? So the effort arm is where you're putting the force in. So it's called effort arm because it's your effort. The other one's called the load arm, and it's over on the other end. We refer to the load as the object being lifted. So if you're applying effort here, you're applying force here, you're pushing down, and this lever moves up. Okay, well, you're lifting this object. So this object, the object you're lifting, the object you're moving, whatever you're moving, is called the load. So the load arm is the arm, or the part of the lever, that the load is on. The effort arm is the part of the lever that you apply the force. That's it. So how does a lever work? Well, work is equal to force times distance, right? We know this. We know that work equals force times distance. And work is measured in joules, right? Force is measured in newtons, and distance is measured in meters. So work is equal to force times distance. If you increase the distance, you increase the work, right? So if I go, oh, I apply a force of 5 newtons. That's my force, right? Right there. And it moves an object, let's say 2 meters. Okay, so we have my force, we have my distance. So my work, 5 times 2, is 10 joules. Easy, right? That's just basic multiplying. Okay, well, as you increase the distance, you can also increase the work. So if I have a force of 5 newtons and I moved it, let's say 5 meters instead, so now I have a higher number, 5 times 5, now I have 25 joules. That makes sense. As you increase the distance, you increase the work being done because you moved it further. This also means that if you wanted to keep the force the same, or if you wanted to reduce the force, you could increase the distance, right? So let's say you only needed to use our previous example, the 10 joules of work, right? 10 joules. That's how much work we need to use or make. Okay, well, in our first example, we had 5 joules, right? We had 5 joules over 2 meters, and that made it 10, right? That made it 10. Well, what if I change it up? What if I instead said, well, let's say I used 2 joules. Let's say I want to reduce the amount of force. I'm tired. I don't want to put that much energy into it. Oh, I put J there. That should be N. Let's say I'm tired. I want to only use 2 joules. I still need to move it the same distance, right? I still need to move this object and make an output of 10 joules. But instead, I'm only going to apply 2 newtons. Well, if I'm only putting in 2 newtons, the distance I'm moving it is 5 meters. The distance I'm moving is 5 meters. Okay, well, now I've just decreased the amount of force I needed. Here I needed 5 newtons. Here I only needed 2 newtons. And that's because I increased the distance. Instead of moving 2 meters, I moved 5 meters. So you can reduce the amount of force needed if you increase the distance. So let's think about this. Which lever is doing more work? So we are pushing down with a force of 150 newtons. And this is the effort arm, right? Because this is the arm we're putting the effort into. And we're putting in that force over a distance of 0.3 meters. Okay, well, and we lift this 150 kilogram weight, this load. Well, again, work equals force, right? Force times distance. Okay, well, the amount of force we put in is 150, so we have 150 newtons, right? 150 newtons multiplied by, okay, distance, 0.3. 0.3 meters. Okay, so let's punch that into our calculator. So you go 150 newtons times 0.3. We created 45 joules of work. We've created 45 joules of work. But we had to put a lot of energy into that. We had to put 150 newtons in. Well, let's check the other lever. Again, same weight. They're both 150 kilos. They're both 150 kilos. But instead, this effort arm is 3 meters long. And our effort, the amount of energy we're putting in, is 15 newtons. Once again, work equals force, right? Force times distance. All right, well, work, how much force did we put in? Well, we put 15 newtons of force. We put 15 newtons of force, okay? And we times it by, well, 3 meters. Okay, well, 15 times 3 is also 45 joules. Oops. There we go, 45 joules. I'm just going to fix this because there you go. 45 joules, right? So when we look at this, they both did the same amount of work. They both did the same amount of work. 45 joules. But the difference is I needed less force for this lever. Right? I needed so much more force to get 45 joules out of this. I needed so much force to get 45 joules. Here, I only needed 15. But the difference is right here. The distance that I was applying this force on was so much greater. Right? 0.3 meters required 150 newtons of force to create 45 joules. 3 meters only required 15 newtons of force. So, when you increase the distance, you're putting your force on, you can get away with using less force. When you're applying a certain amount of force over a distance, the larger the distance, the more work you're applying. So this is how levers make work easier. This 150 kilogram weight could be lifted by only using 15 newtons of force if I have this long arm, this long effort arm. So work in, work out. When you apply the force down to lift a load, the load is also applying force down as well, right? When you have a weight, the reason why it's heavy, it's because it's applying a force, gravity, right? It's applying gravity down onto your lever. That makes sense. Things have mass. Things have weight. Things weigh things because of gravity. So you're applying a force, but so is the object or load as well, right? So to lift any object, if you're lifting a heavy object, you need to beat that gravity, that force, right? So the load is applying its own force onto the lever. So now this leads us to two other terms. We have the effort force and we have the load force. The effort force is the force you apply. You are doing this. You are trying to lift the object by applying the force. The load force is the force applied by the load. Because, again, this has mass. So it's going to apply gravity or gravitational forces or its weight to the load arm. So you have your effort force on your effort arm. You have your load force on your load arm, right? You apply your effort force over this distance to create work. And the load force does the same thing. So what do you notice about this lever? If I were to clear this ink, what do you notice about this lever? About the length of the arms and the load and effort force? Well, hopefully you realize that the effort arm is so much longer than the load arm. Interesting, right? The effort arm is so much longer than the load arm. The load arm. And so if we go back to this one, or this one, you could see that we can generate the same amount of work if we increase distance. So if we increase the distance, we need less work to lift things. Well, if we have a short distance, that must mean you need more force to lift the other way. So this is how levers work, right? The load arm is so small that the load needs so much more force to fight against this side, while this side's so long that you only need a little bit of force to fight against this force. So we talk about this as work in, work out. When you apply your effort, I'm going to put E for effort, right? When you apply your effort onto the effort arm, you're creating work in. You're putting work in, right? Well, when the load is being lifted, it's applying a force, right, over a distance as well. But it's also being lifted. So we call that work out. So I'm going to put WO right here, work out, and WI for work in, right? You're applying a force over a distance, so you're creating a work force or an amount of work in, and the machine is also experiencing work on the load arm because of the force of the load. The load is putting force on the load arm, and the load arm has a distance. So, how much work is being done by the load arm? So, in order to lift any object, the work in must equal the work out. The work in must equal the work out. So, we have a weight, and it's applying 450 newtons over a 0.1 meter distance. So again, because this is the load arm, that's our work out. So we go work, and I'll put a little O there, you don't have to, it's just to keep track of things. Work out equals, well, 450 times 0.1. Okay, well, work out equals 450 times 0.1. We'll punch that in. 450 newtons times 0.1, right? 45. So we now know that our workout is 45. And I should probably put the units in: joules, newtons, meters. Right? So the machine has put out, the work out of the machine has put out 45 joules. Okay, well, how much work was done by this one? Well, this one must also be equal. The amount of work you put in must equal the amount of work done by the load to lift it, or done by the machine to lift it. You could say either or. So the amount of work you put in must equal the amount of work done by the load. So again, we go back here, 450 newtons over 0.1 meters, so we have 450 newtons over a distance of 0.1 meters gives me a workout of 45 joules. Cool. So we have 45 joules on this side. Well, if this is 15 newtons over 3 meters, again, 15 newtons, significantly less force than the load force. So our effort force is 15 newtons over a distance of 3 meters. Well, that's also 45 joules. So we also have a work of 45 joules. That's our work in, our WI equals our 45 joules. So the work put out by the machine and the work done by the load, I'm going to use those interchangeably, is 45 joules. In order to lift this, I also need to put in 45 joules of work. Well, the distance on the load arm is so small, but the distance on the effort arm is so big. So because the distance on the effort arm is so large, we can use less force. And so to get 45 joules of work, which is required to lift this, we only need 15 newtons of force, right? Only 15 newtons of force over a very large distance allows us to lift a very heavy object over a small distance, right? To move this all the way down only lifts this a little bit up. if work in and work out must be equal, what's the point? The effort you need to apply is so much smaller than the load force. So less force is needed to lift the load. So yeah, the work here is 45. The work here is 45 joules, right? The work here is also 45 joules. So they're both doing, 45. They're both doing the same amount of work. What's the point? Well, this object, this load, the thing we're lifting, is applying a lot of force. Is applying a lot of force down. But because we've increased this distance, we only need a little bit of force. We only need a little bit of force to lift it. And that's what levers do. They decrease the amount of force you need to lift an object. So, on your own, I want you to figure out what is the work in or work out. So remember, work in and work out must be the same. So you need to know what is the work calculation, right? How do I find what my work in is? How do I find what my work out is? Where is my load arm? Where is my effort arm? So I want you to know what all those parts are, and I want you to be able to find out what are the missing pieces in each of these diagrams. So pause the video and try and solve it on your own. All right, so we'll do one together. We'll do this first one. So you should know that this is the fulcrum. This is the load arm because that's where the load is. This is where the load is. So this is the load arm, right? The load is here. And this is the effort arm. This is where we're putting force. Okay, so we know that on this side, we are applying a 300 Newton force over 5 meters. So I'm going to say Wi in, work in equals force times distance, so 300 newtons, right? 300 newtons over a distance of 5 meters. Over a distance of 5 meters. Okay, well, we just do that. That should be around 1500, but we'll check. 300 times 5, right? Easy peasy, 1500. So our work in is 1500. And now remember, you need to keep your units, 1500 joules. So we now know our work in. We put in a work of 1500 joules. And if we look at our previous slide, the amount of work in must equal the amount of work done by the load to lift it. So this lever must also equal 1500 on the other side. So we have 500 newtons. So the work out, so WO equals, well, 500 newtons, right? 500 newtons over a distance of something. So I'm going to make that x. Over a distance of x. Well, we know that the work in, this is the work in, must equal the work out for this to work, right? So we can erase the work out and replace it with 1500 because we know it must be equal. Otherwise, this lever is not going to work, right? So we have 1500 joules on this side. So 1500 equals 500 times something. Now, if you know your basic algebra, you have to get the x by itself, so I need to get rid of this 500. I'm multiplying here, so I divide by 500, which cancels and cancels. But whatever I do to one side, I do to the other, 500, right? That equals 300. Sorry, 3 meters, right? So that equals x. So now we know that this is 3. Now we know that the distance is 3 meters for the load arm, because 500 newtons times 3 is 1500 joules. 300 newtons times 5 meters is 1500 joules as well. So to lift this object and to apply this amount of force, you need a 5 meter effort arm and a 3 meter load arm. Okay, actually let's just do one more to hammer this in. So the load is putting a force of 575. newtons over a distance of 5 meters. Okay, well, this effort arm, so we know this is the load arm because this is where the load is, right? So this is the load force. This is the load arm. We know this is the fulcrum. And we have the effort force, which we don't know, and the effort distance, or the effort arm. Okay, so we know that work in must equal force times distance. We don't know what the work in is, so I'm going to make that x times 25. Okay, let's see if we can find our work out. Work out equals, well, 575, right? 575 newtons. So I'm running out of room. Times 5 meters. Perfect. So work in must equal work out. Well, we have this calculation we can find. So we have work out, which is 575 times 5, which gives me 2,875. So now I know my work out is 2,875 joules. Cool, that's my work out. Well, again, for a lever to be efficient, work in must equal work out. So work in must also equal 2,875. Right? Equals x times 25. Okay, so basic algebra again. I want x by himself. I'm multiplying, so I divide by 25. Whatever I do to one side, I do to the other side. So I divide by 25. Sorry, this is taking a lot of room. So we got 2,875 divided by 25. Boom, 115. So we know our force must be 115 newtons equals our effort force. So we know that this must equal 115. 115 newtons, sorry. That's a lot less force, right? This load, this weight, needs to apply 575 newtons on this arm to fight against this. But we only need 115 newtons to lift that, right? Again, this immense distance reduced the amount of force we needed to lift this object. So here we have a real life example. This is a car jack. Mechanics use this to lift a car, right? So a jack can be used to lift one side of a car in order to replace a tire. To lift the car, the jack handle moves 30 centimeters for every 1 centimeter the car is lifted. So when you basically pump this jack up, when you apply a force to make this jack push the car up, let's say this moves it down. This moves down 30 centimeters. 30 centimeters. Okay. Well, when you pull it down 30 centimeters, this part, the thing that lifts the car, only moves 1 centimeter. Okay, what force is applied to the car by the jack? So you can assume all of the input work equals the output work, right? Assume the input work equals the output work. So when you pull down on this lever, on this side, the lever has to move 30 centimeters down for this side to move up 1 centimeter. Well, we could redraw this like a lever, right? Like so. Well, which side are we putting our force on? This arm, right? And we know it's 30 centimeters. Well, if it's 30 centimeters, then we know it's 0.3 meters, because you got to keep it in units, 0.3 meters. Okay. And we apply a force of 150 newtons. So we have a force of 150 newtons on this side, right? So we have an effort force of 150 newtons. Let's make this a bit bigger. So we got our lever right? We are applying 150 newtons of force. We're applying 150 newtons of force from here. We know that the lever, this arm, moves 30 centimeters, right? But our calculation must be in meters. So we just convert that into 0.3 meters. Perfect. So we know this is our effort side because this arm is where we're putting the force on. Well, the car is on the other side. So I'm going to put this box as the car. That's a car. That's our load, right? And this arm only moves 1 centimeter. 1 centimeter, so 0.01 meter, because that's 1 centimeter, every time this moves 30 centimeters, right? So what is the load force? How much force is the car applying? Well, let's find our work in. Our work in is force, newtons, times distance. So we have 150 times 0.3. Well, that's 45 again. Yay. Right? 45 joules. Well, work in must equal work out. So we have work out, right, equals the force we're looking for. So I'm going to make that x times 0.01. 0.01. Well, I know my work out because work out and work in must be equal. The input work, or the work in, must equal the output work. So we know that this must also equal 45 joules. Right? Well, again, divide, work out equals 0.01, 4,500. So we have 4,500 joules. No, sorry, not joules. 4,500 newtons. So we know that the car is applying a force of 4,500 newtons. We're putting in a force of 45 newtons. The car is putting in a force of 4,500 newtons. Now, the car only goes up a small distance. We have to move it a huge distance. But we get to use less force. So it's a lot easier for us to lift the car because we are moving the effort arm 30 centimeters to lift the car, or the load arm, 1 centimeter. So hopefully you see the relationships between the two and see how if you increase the distance of the effort arm, you need less force, right? And the load arm tends to be smaller than the effort arm. So you need to know fulcrum, the turning point, the effort arm, the arm you're putting your effort in, the load arm, where the weight is, the distance the arm is where the weight is, and then you have your effort force, the force you put in, and the load force, the force applied by gravity on the object, or the force of the object. You need to know that work in and work out must be equal, right? Because the force of the object is applied onto the load arm, which is a distance. So you have a force over a distance. That creates work. And you're applying a force over the effort arm, which is a distance. So that also creates work. So we call the work you do work in, because you're putting the effort on the effort arm over a certain distance. And we call the work done by the machine the work out, right? Because the load is applying a force over a distance. So they must be equal. Now you might be asking, why should the work be equal? Why shouldn't the machine do more work, right? If the machine does more work, isn't that easier? Not necessarily, right? What that means is if the work you put in is more or less than the work put out by the machine, then the machine's being inefficient, right? It's using more energy, it's using more force to lift your object, right? And so it's a waste of space because, again, to reduce the amount of force, you need to make this effort arm longer. If you make that effort arm longer, it's bigger and it can be more inefficient. So making the work in and work out equal, making them equal, maximizes efficiency. So hopefully this made sense. It's a bit of a confusing lesson in terms of, oh, work in, work out, effort, and so on. But you just need to know what work is. You need to know the parts of the lever. And you need to know that the work done by the effort side, the effort force and the effort arm, equals the work done by the load arm and the load force. And so if you can make them equal, you know how to do these questions. So hopefully this was helpful, and I'll see you next lesson.